I've spent a lot of years out in the field, in the crawl spaces, in the attics, crawling and sweating, spending day after day working my fingers until they bled, through cuts, through rain, through all sorts of conditions. I never thought there'd be another side to who I am. I never thought there'd be another chapter. It was with some frustration that I went from day to day, because I didn't know what came next. And now, 25 years later after starting as a young child, a 14-year-old working in the summertime, another chapter is coming. And I hope all of you guys come along with me to enjoy it. My name is Zack, and this is The Tradesman. Welcome back to The Tradesman, you guys. Glad to have you back for episode 3. This week is going to be a little bit different than our previous episodes. On the last couple episodes, we've had multiple interviews in the same show, but this week, we're going to have one big, long interview from Mr. Jim Bergmann. Now, Jim's been on several podcasts. He's on HVAC School podcast with Brian Orr. He's been on the Working Joe's podcast with me and Ralph Wolf. But he's going to come on this podcast today for a little bit more HVAC learning. Now, Jim's been a tradesman for a long time. He worked in the field. He had his own company, Bergmann Enterprises, years ago. So he knows the ropes in the field, but he also understands HVAC more than most other people alive. So we're going to talk about what started as a simple conversation about temperature split. Now, for guys that aren't in the HVAC field that are starting to wander away from this podcast, let me tell you, it's an interesting conversation. It is technical, but it's very interesting to understand how temperature split on your HVAC unit is affected by different factors, including the air going through the machine, the air outside of the house even. So it's really cool to hear how he breaks it down. Now, here's the things you're going to require for today's podcast. Of course, you can just listen to it and hope you glom on to whatever information you can. But if you're an HVAC and you want to learn more about this, it might be nice to keep a notebook handy, because notebooks will help you get through this podcast better. You can write down the things Jim says. You can read them 150 times. You can listen to the podcast 13 times, because it is complicated stuff. But I tell you what, guys, if you follow along with us, you will understand a ton more about airflow and, in turn, mass airflow. Pounds of air moving through the system. That sounds kind of strange, because we always talk about CFM of air. We're talking about pounds of air moving through the system. And he's going to tell you how many pounds move through the system, because everybody says, air, it doesn't weigh anything. But it actually does. And we're going to talk about that. Before we get into that, we interviewed Curtis Bowers last week. We're going to put on a little tidbit of that interview that didn't make it to air last week, where me and Curtis talk about the Trane replacement coils and how they make you want to pull your hair out. So before we get into Jim, let's listen to our hair-pulling adventure with Trane evaporator coils. Trust me, I go to buy a Goodman coil the other day, an air handler coil, and the coil's $276 for the air handler. That makes sense. That's about right. That's great. I go to buy a Trane coil from the American Standard Parts House, and keeping in mind that my father's an American Standard dealer steel, so they should have good pricing on the parts. I just use his account and pay him. Yeah. So the coil with a TXV, I've had one that was $900, one that was $1,400 for the coil. The air handler cost like $500 back in the day. I don't know what happened in between then and now, but that really appreciated nicely for Trane. You know what I'm saying? They must have really invested in the right coils. They've grown nicely over the years. I know about the 3-week waiting period. I've had a customer that just jumped ship because I said, well, it's going to be like a month. It was the same coil. I ordered 2 of them. And they're like, well, both of these have to be manufactured. I'm like, what? You have to build the coil? I mean, can we go out back and build it? He's like, no, that Trane has to build it. I tried to build one. It really looked bad, Curtis. No, Trane has to build it. And it took like a month, and one of the customers actually just changed their systems with somebody else. They were ticked at me, and they changed their whole system, both of them in their house.
You couldn't sell them a new system?
They didn't want a new system at first, but I guess they were so soured on their experience with me that they decided to hire somebody else
but
and
it
change
wasn't
both
your
systems.
fault. But it wasn't your fault, man.
No, hey, such is life, right? It's the funny thing about going to the supply house. You go to a Goodman supply house, you get a price on a coil. You go to a Rheem supply house, get a price on a coil. Same thing across the board. You never know what you're going to get into. I've seen evaporator coils that are as low as $200 or even a little bit less, all the way up to well over $2,000 on the residential side. No explanation on why, whether it's difficulty of manufacture, whether it's the fact that it's not manufactured until there's a demand. I don't know. Evaporator coils that are so high priced that if you buy the air handler that they are part of, it's cheaper. So you can literally buy the air handler and take the coil out of it and replace it, and it's cheaper than buying the evaporator coil by itself. Staggers the imagination. Same thing on the heating side. Heat exchangers for gas appliances, I've seen them $150, $160. I've seen them go well over $2,000 just on the residential side. And we're talking a Goodman and a Rheem on that. So you never know what it's going to be. Goodman's typically on the lower end, which is good and bad. We can debate that at a different time. That's not really what this is all about. What this is all about is Mr. Jim Bergmann. He's going to talk temperature split. He's going to get real in-depth. More in-depth than I planned on. I planned on doing an interview roughly half the size of the one we actually did. But we got fired up, we got going, and it was a good learning experience, and I hope you guys, especially you HVAC installers, company owners, and techs out there, get a lot out of this. We're going to bring Jim back in the future to talk some more, maybe about actually making the measurements, but today we're talking about the science and the math of temperature split. One of the reasons I wanted to talk to you about temperature split is because the guys, it seems like it happens all the time. Guys will be online in these groups going to war with each other, saying that you need to get a 20-degree split, you need to get a certain amount of split. And of course, we both know that's not true. So how do you communicate what kind of split you need based on a guy that may be brand new, that if you start breaking out some of the actual calculations, he's going to just grab his head and run off in the other direction? How do you introduce somebody to figuring out what the split should be?
I usually start with a target temperature split chart. If you go to TrueTechTools.com and do a search on there for how to charge an air conditioning system, or just type in Google how to charge an air conditioning system, and you'll find a link I put up there years ago that has a link to a target temp split chart and a fixed orifice charging chart. And that's usually where I have people start at, because the temperature split can be anywhere from 16 to 28 degrees. There's a lot of variables in there, and even a lot more than a standard temp split chart will tell you about. We can cover some of those things.
One of the things I want to talk about, because we actually talked about this the other day on the Working Joe's podcast, that your new calculations are going to include liquid line temperature and other factors that the previous calculations did not include. What factors play into what the split is going to be?
Well, there's a lot of factors. I mean, the primary drivers are on temperature split are the return air wet bulb and the return air dry bulb. We're going to remember on an air conditioner, we are removing heat and humidity. And any time that we're condensing the water vapor out of the air, that's work that the air conditioner is doing. It's latent load, and that latent load robs the system of temperature split. And until you get the latent load out of a home, you really don't get the maximum temperature split of the equipment. In fact, a lot of the work the air conditioner is doing goes to latent capacity control. And if you get like down in Florida and places like that where it's high humidity and high temperature, latent load plays a huge factor in the temperature split as far as reducing it down to that 16-degree range, where if you're like in Arizona and there's no latent load, it could be 28 degrees temperature split across the evaporator coil and be totally fine. But the big factors are heat and humidity, and then the secondary factor that a lot of guys don't consider is the temperature of the liquid line itself. Some people tell you it's outdoor air temperature, and outdoor air temperature is a driver because the outdoor air temperature is what makes the liquid line temperature go up and down. But so do things like a dirty condenser coil. When the condenser gets dirty, and the liquid line gets really hot, the liquid's got to go through the metering device, and it gets cooled down to the saturation temperature in the evaporator. And that flash gas, there's a certain amount of refrigerant that's called flash gas that flashes off to get cool the liquid down to its saturation temperature. And the more flash gas we have, the less the temperature split's going to be, because now we're using energy to cool that hot liquid down to the saturation temperature instead of cooling the hot air down to the supply air temperature, right? So that plays a factor in there too.
So if you have a unit and you have guys out there that are servicing stuff that was put in yesterday, servicing stuff that was put in 1985, you have a unit that was put in 1985, let's say it's 8 SEER, it runs a little bit hotter, so to speak, than a unit that's put in yesterday. Do they approach temperature split differently between those two units?
Well, they're both going to have the same, so let's just hit that for just a minute. So let's say you got a 6 SEER, a 10 SEER, and a 24 SEER piece of equipment. They're all rated at 2 tons, right? Well, they're all going to do 2 tons of capacity. Even though the older system's got a hotter liquid line than the newer system does, they're still going to do 2 tons of capacity. It's just the amount of work they're going to do that 2 tons is going to be different. In other words, one's going to consume a lot more power to do the same thing, right? Because it's got that higher liquid line temperature. They've got to include that in the capacity of the system, because you got to not only reject the heat that we absorb at the condenser, but we also got to consider the heat that's coming back in the liquid line, because if the heat's not rejected, it's coming back in the liquid line back to the metering device, and it's just heat that's circulating throughout the system, more or less. When you look at also what affects temp split, well, obviously, we talked about return air temperature, return air relative humidity, the biggest drivers. Liquid line temperature is a secondary factor in there. In the applications, we actually do take that into consideration, because when you look at the temperature split, the charts that you typically see out there, those are based upon a specific SEER of equipment and a specific temperature, because and typically that's when you go, what we design for is what we call AHR, design conditions. So that's 95 degrees outdoors, 80 degrees return air dry bulb, and 50% relative humidity. So when you look at those charts, they don't take into account the fact that as the outdoor air temperature changes, you're also going to get a higher or a lower split. So above 95, we expect to see the split lower, and below 95, we'd expect to see the split higher. Because if the liquid line's cooler, there's more energy that can be converted to comfort cooling at that point. So you're going to get a higher capacity out of the coil with a lower liquid line temperature. Just because you're not, again, cooling that hot liquid down, you're cooling the air down, and you're going to get a higher temp split out of that system.
Are you going to see any differences between a TXV and a piston? Because obviously if it's a different temperature outside, it's going to affect the superheat on a piston, but a TXV is going to adjust to keep a relative same superheat. Is there going to be a difference in the target temperature split?
There will be slightly. That's another factor that plays into place, but not near as much. I mean, when you get a cap tube system that's way out of its range, in other words, you're running 30 degrees of superheat, and that's the target superheat. Yeah, that's going to affect the temp split on the coil for sure, because now you're talking about a bit of the evaporator coil that's not fully active. In other words, all the refrigerants change state, and we're picking up additional superheat in the evaporator coil, as it goes towards the compressor. But as that superheat approaches 10 degrees, which is the target superheat for a typical fixed orifice system, the target meaning that at design target, not the fixed target. The target on a fixed orifice is all over the place depending on the load. But when we go back to 95 degrees outside, 67 degree wet bulb at 80 degrees, I think your target's somewhere around 13, 14 degrees of superheat. When you get down to 75 degrees, I think we're around 10 degrees superheat. I'm just going off memory. When you look at those charts, you can see exactly where they're right around 10 degrees of superheat. That means you're going to get full capacity out of the coil. But the split will vary a tiny bit. But when you're looking at an evaporator coil, the superheat is really picked up in the last 1 or 2 passes of the coil. So even at 35 degrees of superheat, most of the evaporator coil is fully active. It's just the last couple passes or not, and that's where we get our additional superheat. And the superheat in the last couple inches, vapors pick up heat much faster than liquids do, because all the energy, all the conversions already happened, and now that vapor just picks up that heat in a very short amount of space. So yeah, it will affect temp split, but not that much. The other thing that'll affect temp split is air density. People don't consider the air density because air density also plays a role, because the denser the air is, the more energy it takes to pull the heat out of that air, right? Most fans, they deliver a constant volume of air with a variable mass flow rate. So as the air density goes down, you have fewer pounds of air going across the coil, which means you're going to get a higher temp split across that coil also. So that's another factor that plays into that, is the air density. And also what plays a factor into it is just simply the evaporator coil selection. Like if you're at 350 CFM per ton, 400 CFM per ton, or 525 CFM per ton in a high sensible environment, that is also going to affect the temp split across the evaporator, is how you configure the system and the airflow that you select off your extended performance tables when you're doing your heat loss calculation. When you're thinking about target temperature split, right, the best place to start at is to understand that everything we do in our industry is about mass flow rate. So when we're talking about cooling air, it's not really about cooling the CFM of air across the coil. It's actually about cooling the mass of air that goes across the coil. So when you're looking at the density of air, let's just start there. A cubic foot of air weighs 0.075 pounds. So it's 0.075 pounds per cubic foot. So when you take 0.075 and you multiply that times 400, you're going to get 30 pounds per minute per ton. So that's the mass of air that's going across the coil, is 30 pounds per minute per ton. And it goes back to, everybody's heard in the industry, the amount of heat required to raise 1 pound of water, 1 degree Fahrenheit, is 1 BTU. Okay, and we know the specific heat of water is 1. That means when we talk about specific heat, that means the amount of heat required to raise 1 pound of a substance 1 degree Fahrenheit. The specific heat of air is 0.24, and it stays pretty constant from about negative 58 to 104 degrees. So it's always going to be at that 0.24 range. So the amount of heat required to raise 1 pound of air, 1 degree Fahrenheit, is 0.24 BTUs. So if we start with that premise, and then I'm going to give you one more formula just to muddy the mix a little bit. But the quantity of heat, okay, when we go back to Chapter 1, Refrigeration, Air Conditioning Technology, I believe it's Chapter 1, it might be Chapter 3, but it's quantity of heat equals mass times specific heat times degrees of change in temperature, right, delta T. So when we talk about 1 BTU, if you plug it in a formula, 1 BTU equals 1 pound of water times 1 BTU per pound times 1 degree Fahrenheit. So that's your formula right there. And that's 1 times 1 times 1 is 1. So it takes 1 BTU to raise 1 pound of water, 1 degree Fahrenheit. Well, if we take and we plug that into standard air conditioning, we say, okay, well, the first thing we got to do is we're going to say, okay, you got 12,000 BTUs equals, we just said 30 pounds per minute per ton, right? 30, right. But we got to multiply that times 60. Why do we have to multiply that times 60? What's on the left hand side? It's 12,000 what? BTUs per
hour.
There you go. Times per hour times the delta T. So what we're going to do is we're going to just figure out what delta T is right here, right? So we know that 30 times 60 is 1,800. So 12,000 divided by 1,800 divided by 0.24 equals 27, right? About 27.7 degree split across the evaporator coil. So if we were to take and calculate out, if we did no latent cooling at all, none at all, we'd expect to see about a 27 degree split across our evaporator coil if 100% of the cooling was sensible. You follow me?
Yes, that's fantastic. I've never thought of it that way, or never put that together, that would be sort of your maximum expected possible cooling split.
That's if all of the cooling was sensible. Now, most of the time, all the cooling's not sensible, is it? So if you were to go and you were to say, what's our typical our temperature split across the coil is what? So just jot down that 27.8, right? So if we took the 20 degree splits that most guys are looking for, divided by 27.8, that's going to equal 7.72. 0.72, okay? So if the maximum split's 27.8 and the typical split is 20, right? That means now, what is temperature split, Zach? Temperature split is what kind of cooling? What is that? I'm going to quiz you a little bit here, make you work for this.
Oh, geez. Okay.
Is it sensible cooling or is it latent cooling?
It's sensible cooling.
It's sensible cooling. Good. All right. So if the maximum cooling we could get was 27.8 degrees, right? And we're only getting 20 degrees, and that's 20 divided by 27.8 is 0.72, right? That means 72% of the cooling was what?
Sensible.
And the balance is?
Latent.
Okay, so that means that if we're looking at a manufacturer's chart and it tells you the total sensible split or the sensible latent split is 0.72, that means that on that cooling system that 72% of the work is going to be sensible work. So we're going to expect to see about a 20-degree split across that evaporator coil on a one per ton, right? Doesn't matter. Here's the other thing. Let's talk about this for just a minute, just to get this clear. If I have a 1-ton system and a 5-ton system, they're both going to have exactly the same temperature split. Why is that?
That's a good question. It seems obvious. Let's see if I can figure out a way to actually say what's in my brain. Because they're doing the same work per ton.
Right. Okay, so what happens with airflow? On a 1-ton, how many CFM are required?
400.
And on a 5-ton?
2,000. So
the ratio of, because 1 ton's 12,000 BTU and 5 tons 60,000 BTUs, the ratio of CFM or pounds per ton of cooling stays the same, right? If you were to take that same system and you were to say, okay, it's 30 now times 5, you get 150 pounds per minute across the coil times 60. That's 9,000 pounds of air per hour. And this is like physical mass. I mean, this is like 9,000 pounds. If you could compress all that air into a cylinder, right, that cylinder would physically weigh 9,000 pounds.
That's interesting.
Yeah. So think about that. That's pretty cool stuff when you think about that. If you take, people don't think about the air has mass. I mean, but you can feel it. If you ever take a piece of cardboard, pick up a big piece of cardboard and try and fan it through the air, you feel the mass of the air pushing against that cardboard as you're trying to displace it. The reason we don't feel it around us most of the time is because we're like in a sea of air and it's just moving all around us. So as we move through the air, all we're doing is displacing it. And so we don't really feel the resistance of it. But you get on a motorcycle and you're going 60 miles an hour, you definitely feel the resistance of the air, right? You take your hands off the handlebars for a minute and you feel like you're going to blow off the bike. And that's the weight of the air pushing against your body. It's the same thing here. So it's all mass flow rate formulas. And I didn't learn this till probably maybe 10, 15 years ago when I started teaching and I saw these formulas in the textbook and started to understand a little bit more about mass flow rate and how all these formulas work together. So everything we're doing here it comes down to that. So now let me ask you a question. We just talked about the fact that that on that temperature split chart, if the target temp split and that 20 degrees that I just gave you, that's based upon a 80-degree dry bulb and a 64-degree wet bulb, we'd see a 20-degree split across the evaporator. Now, when we talk about 80 degrees and 67 is design, that's about a 17-degree split across the evaporator coil. If we go into 75-degree air, which is typically what we would see, 65 and 63, we'd be about 18.6 degrees across the evaporator coil is what we'd expect to see for a target temperature split on there. All right. But this entire chart that you're looking at off this 2005 residential manual here is all based upon a latent sensible split of 0.72, right? So that means 72% of the work is going to sensible. If we go to our extended performance tables, you can have a sensible heat ratio anywhere from 0.60 to 0.68 to, let's say, 1.0, right? As we're in Arizona, we want to see 100% sensible cooling. If we're in your neck of the woods, right, we'll probably want to see it closer to 0.70, 0.72. We might even see it at 0.68. All that varies. That target temperature split's going to vary with the airflow requirements. And a lot of guys just don't understand that. That's where a software tool like MeasureQuick becomes extremely handy because it's going to calculate all those all those variables for you and get that target temp split correct.
So basically, guys that are listening to this that have a sheet of paper out, or maybe they threw the paper down about 10 minutes ago, are thinking to themselves, perhaps we'll just get Measure Quick and not worry about this.
that is one way of doing it, and I'm not trying to plug the software, but I am telling you, even myself, I didn't realize how complicated calculating out what a target temperature split should be on an air conditioner based upon how we commission the system would be. And then obviously when you look at the deviation from the target temperature split, because typically we say plus or minus 3 degrees, that also plays a big factor. Because let me just ask you a question here, because you're pretty good at math. If I tell you,
Pressure's on.
I know I'm going to push it hard on you here. If I tell you that, just think about it this way: a question's on a test, right? If there's 100 questions on the test and you miss 3, you've only missed how many percentage?
3%.
What if there's 10 questions on the test? How many have you missed?
30%.
30%, right? So if the target temperature split is, let's say, 20 versus 28, does that 3 make a bigger difference when it's 20 than it does when it's 28?
Absolutely.
Absolutely it does, yeah. So when we say plus or minus 3 degrees, that's actually not a good way of doing it either. We should be looking at plus or minus a percentage of the airflow, which typically is 10%. So when we say what our target airflow is, we want to say plus or minus 10% of 400. So anywhere from 440 down to 360 is where we consider the airflow range typical for an air conditioning system when we go plus or minus that 10% of the target CFM. That's the other thing when we're doing these calculations, when you're at a very high latent load, right? Because what do you think is going to happen to our target temp split when our latent load goes way up? In other words, we have all this humidity in the house. What do we expect to see happen to the target temperature split? To go up or go down?
It's going to go down.
It's going to go way down, right? I'm sure you started a system when it's 80 degrees outside, and I'm sure you've probably started when the return air is approaching 70 degrees of wet bulb temperature. Well, that target temp split could be 15.5 degrees, right? So 15-degree target temperature split. When you're setting up that piece of equipment, if you got the target temp split set perfect at 15 degrees, and then you were to come back when the house got down to satisfied, and let's say it got it down to a 75 degrees at a 60-degree wet bulb, then we'd see a 20-degree split on the same system. So without an adjustment of airflow, just because the humidity dropped down into the house, that we went all the way from a 15-degree split down to a 20-degree split, and all that changed was the relative humidity in the home. As the relative humidity drops in the house, there's less energy going to convert the water vapor in the air to water, and more energy then goes to cooling the air down, and that's why we see a higher split across our evaporator coil. You definitely, at minimum, you want to get one of these target temp split charts. Use that as a tool to get you in the ballpark. That's very, very helpful. The best thing we can do today is, in my opinion, is install equipment with ECM blowers and set the airflow directly on the ECM. But I've even run across challenges with that with guys. I had a customer not too long ago, went on a consulting project. Guy flew me down to Memphis, Tennessee, having problems with the job. Lady's got a historical home. Floors are buckling. She's got dehumidifiers running in her house because the humidity is so high in the house. I went down there. He tells me, "Oh, I've got everything set perfect. I got 350 CFM per ton. I set all the dip switches right. It's just not working right." I go down there and look at the dip switches, and sure as heck, he's got it set for 350 CFM per ton, but he's got a 3-ton unit and he's got a 5-ton drive, and he had it set for 5 ton of cooling. So instead of, if you took that down, what is that, 5 times
5 times 350 is 1750.
Yeah, 1750 instead of 350 times 3, right?
Wow, ton of difference.
Yeah, so he's got airflow way, way too high. He's got the thing set up for all sensible cooling just about. Switch that dip switch, got down to 3-ton drive. Boom, things cooling like a champ. Humidity is one of those things that if you don't have the dip switches right or don't have the airflow right, you could play havoc either way. Because here's the other question for you. And here's why temp split is so critical, absolutely so critical, is if the airflow is low, right, what happens to the temperature of the evaporator coil? It does what?
It goes down.
It goes down, right? Well, the evaporator coil goes down, falls below the dew point temperature of the air. So when the evaporator gets colder, what happens to the amount of moisture removal? It goes what?
It increases.
It increases, right? So if the moisture removal increases on your evaporator coil, and we just went through this whole exercise explaining that moisture removal is at the sacrifice of sensible capacity. What happens to your sensible capacity in the machine? As they slow the fan down, the coil gets colder, we're moving more humidity. What happens to sensible capacity in the machine?
It decreases.
It decreases, right? What's the only thing the thermostat measures? What kind of heat does it measure? Sensible heat. If your fan's gone down too slow, your filter's dirty, your system's got low airflow, and you could be dehumidifying your house like crazy, but guess what you aren't doing? You aren't cooling it off. So guess what happens? That system runs forever because it doesn't have a comfort stat on there. It doesn't know that the humidity's down to 40% in your house and it's 80 degrees and it's actually comfortable. All it knows is it's 80 degrees and you got it set for 75, and it's going to keep running and running and running and running because it can't satisfy the sensible load, right? Getting the airflow correct and getting the correct quantity of sensible heat is absolutely critical, because you can have a system, you can have a 5-ton system you put in. And this is an interesting thing that happens all the time. A guy puts a 5-ton system in, and it's got really low airflow because it's got a lousy duct system, and it's got an old PSC motor. And he goes, "Oh, there's 5-ton in here. I'm going to put a 5-ton. I'm going to take it out, put another 5-ton unit in." And all of a sudden, it's running way differently than the old one did, right? Well, what happened? Well, what happened is probably got an ECM blower in there. The airflow, if it can overcome the duct system, if it's not that bad of a duct system, now the airflow increases. When the airflow increases, guess what else happens? Your sensible cooling increases. And now you can have a system that before might have seemed like it was moderately sized for the house. Now it's oversized for the house because our temperature split, or our sensible cooling, went way up on that machine. And when we have an increase in sensible cooling, we're going to short cycle on the thermostat. And that's how you can have, exactly the same system, pull one out, put a new one in, and you can actually see tremendously different characteristics of operation. And it all comes down to fan speed and a change in temperature split across the evaporator coil. Because you've gone from 25, 26, 28 degree split down to a, down to a 20 degree split. So now what you're doing is, because you also got to remember, when you're looking at sensible cooling, you also got to look at your airflow. As your airflow drops down, your sensible cooling capacity is going to drop. You're going to shift over to latent cooling. It gets crazy when you start thinking about all of it, and it can make your head explode. But the key thing here is you got to get those airflows right. You got to get those splits right. You got to use a target temperature split chart, and you got to understand that the split will vary with the relative humidity. And if you're just setting things up for a 20 degree split, you're going to have a heck of a mess on your hands, because if we go back, if our target was 15 and I set it up for 20, what did I just do to my airflow? Is it too high or too low?
Target's 15, set it up for 20.
Yep. So let's say it's hot and humid in the house, and the split should be 15 degrees. And I set it up and I got a 20 degree split. Is my airflow too high or my airflow too low?
Oh, it's definitely too low.
It's definitely too low, right? So I have this low airflow. I'm wringing moisture out of the house like crazy and dehumidifying, but I may never be able to satisfy the sensible capacity of that machine. Just think about this for just a minute. If I'm off 5 degrees on my temperature split, right? Because if I'm off 5 degrees at high load, I'll probably be off 5 degrees at low load. Probably pretty much the same ratio, right? If I'm off 5 degrees, as a percentage is, if I look at my target's 20 and I'm off 5, I'm at 15, right? What percentage is that? That's 25% of my sensible cooling is been converted over to latent. And sensible is what, again, controls the thermostat, and that means that, guess what? It's not a 25% increase in runtime. It could mean a 100% increase in runtime, because if I can't satisfy the sensible load at 95 degrees, let's say, if it's designed, if I can't satisfy it, it's going to run forever until the temperature drops outside. So just increasing that airflow and getting that split right could literally be the difference between a machine that runs constantly and a machine that now cycles off all the time because now it can satisfy that sensible load.
Absolutely. But man, it was dry in there.
It gets to a point though where, and people are a little bit wacky about temperature because they get in their head, oh, it's got to be set at 72 in here. It's got to be set at 74 in here, whatever temperature. They can be sitting there freezing to death because the humidity is so low in the house. I was just over a lady's home. She's getting nosebleeds in the summer, and she's putting a humidifier on in her house, in her bedroom, because she's getting nosebleeds because the humidity is too low in the house. And it all comes down to, she's got a 26, 27 degree split. This thing, she's got a pretty tight home, so she doesn't have a lot of air infiltration, but she's got a lot of heat load, cathedral ceilings, and she's trying to get the temperature down, and the humidity's dropping so low she's having nosebleed problems in the summertime, and adding humidity to her house. And all honest to God, all it requires is just getting the blower speed correct. In this case, we can't do it because she's got a ductwork issue, and their ductwork's way undersized for the house. But you understand how all this stuff sort of interrelates now. It's pretty interesting when you get to it. So
it is, and that's incredible.
I apologize for blowing your head up on such a simple question, but sometimes the answers are more complex than we really want them to be. But honest to God, it's the truth. I mean, this is the kind of stuff when this is what separates your top technicians from the rest out there. It's the guys that can solve these kinds of problems, guys that understand how to use these tools like target temperature split charts, and guys understand that temperature split shouldn't be 20 degrees all the time. It varies with the latent load, and guys use the right tool for the job. And that's really what it all comes down to.
And it's nothing that's that difficult to get started with. I mean, like you said, you could just use a chart to go by the chart until you get a grasp of the math, if you even want to get a grasp of the math. And you can be all set just by referencing these charts you've already given them earlier in the podcast.
Yeah, right. Just go TrueTech Tools. It's like I said, it's a free download. It's under how to properly charge an air conditioning system or how to charge AC units. It's actually TrueTech.tools.com/refrigerant charging. And if you scroll down there a little bit on there, you'll find the non-TXV charging guide. It's right below. There's a picture of some evaporator coils. Right below that, you'll see the non-TXV charging guide, and that's the download you want to download, and that'll get you started on using that target temp split chart. And that's a great chart to start with. I mean, it'll get you. I would say if we're talking percentages, it'll get you 90% of the way there. These other things we're talking is about tweaking, is about fine tuning the target temp split versus just getting it in the ballpark. But even getting it in the ballpark will get you, like I said, 90% of the way there. Make a huge difference in the performance of systems. Probably the biggest frustration some of you guys are going to have out there is you're going to figure out that you cannot get, even on high speed, you can't get the target temperature split where it needs to be. And that goes back to most of the time improperly sized ductwork. The other thing you might find is that people are using these pleated filters. They have huge static pressure drops across them. You'd be better off going to a filter that stops rocks and bumblebees, one of those old fiberglass throwaways, and getting that airflow correct, because that'll save your customer a ton of money. Once that evaporator's working right, I don't know if you've ever pulled evaporators out, Zach. A lot of times you see some of them they're 30 years old and they're spotless. They're absolutely spotless, right? That's because they're self-rinsing, right? If you're getting good humidity on that coil, it's constantly running water off. It's carrying the dirt down the drain. That's why condensate drains get plugged, is because the filters aren't catching all the dirt, and some of the dirt gets trapped in the condensate. But it keeps the evaporator coil nice and rinsed. And sometimes you'll see some evaporator coils that are they have a swath of dirt at the top of them. That's because the evaporator coil wasn't fully active. In other words, it had a low charge most of its life, and that dirt collecting at the top is because that part of the coil was dry and it didn't self-rinse all the time. There's always this little key, indicators you can see how that system was running when you go tear the old one out. That's why some coils are absolutely spotless, though, when you pull them out and they're 30 years old, because you had a fully active evaporator and it was constantly wringing water off that system as it went. So pretty cool stuff.
I think about the General Electric ones. Whenever you said that, I think about the General Electric coils with all the wide fins, and they'd be perfectly clear after all these years.
Well, and here's the other reason why, because those had Aeroquip fittings on them, right? A lot of those old systems had those old Aeroquip fittings. Well, guess what? The coil came charged from the factory, the line set came charged from the factory, and the condenser came charged from the factory. So the refrigerant charge was was more or less perfect on there. Back in the day, everybody charged by weight. If you go back and you look at the old textbooks, just get an old textbook out from the 70s or 80s, you'll find out it doesn't even mention superheat or subcooling. It doesn't even talk about charging a system or how to charge a system. A lot of textbooks don't cover charging a system, which is amazing to me still. But they did it all by weight back then. So as long as you got the charge right and you got the airflow right, you were in pretty good shape. That thing would wring water and self-rinse and worked great. But that target temperature split is absolutely critical. And download those guides and play around them, and you'll be a lot better technician in the long run. And sorry to put you through all the pain of the math, but I wanted you to see where that target temp split comes from. And theoretical maximums 28-degree split across the evaporator, but it could be as low as 15 and be totally fine. That means half the energy. Think about that for a minute. If you go from a 30-degree split to a 15-degree split, half your energy is going to dehumidification. Half of it. So if you got 24,000 BTUs, 12,000 BTUs is dehumidifying and 12,000 BTUs is cooling. And guess what happens as that humidity comes down in the house? Now that 12,000 BTUs that was latent, now all of a sudden it's up to 18,000 BTUs is sensible, and 6,000 BTUs is latent cooling. So that's always shifting around. The amount of BTUs that are devoted to sensible to latent, and it's all based upon sensible latent split. And that's how it all works.
Well, I'll tell you something. Whenever we started this, I didn't know really where it would go. Oftentimes we'll do this sort of thing. I don't know what I'll learn, what we'll talk about by the time we're done. But as you went through the formulas, and I sort of looked at them for the first time, some of the stuff for the first time. I've read about it, I've heard you talk about it, but seeing it for the first time, I'm happy to say that some of it actually clicked. People are always waiting for that. I'm always waiting for something to click and piece together several different pieces into one. And it really did. Just knowing the maximum temperature split, seeing how that arrived, mass flow instead of CFM is something that I've wanted to learn about, but, being in the field and wanting to devote time to learning about it, it's difficult sometimes. But I'm happy to say I hope it clicked for other people out there, because it definitely clicked for me, and I appreciate that.
Yeah, cool. Well, I'm glad you got something out of it. And I'll send you what I might do is sit down and jot the math out by hand here real quick for you, just to show you how all the units cancel out, because that's another interesting thing is when you understand how all the units cancel. Maybe you can put a post up somewhere on Working Joe's or something where guys can see. I'll just do it by hand real quick, just do the math, and that way people can see how everything cancels out, how the units work.
All the techs out there, I know a lot of you guys who are listening to this, a couple of you, like I said, threw your notebooks down like 15 minutes ago and swore. And some of you are probably rocking on the side of your bed wondering what's going on. But it's the same way for me. Once you get into it, go over it again and again, listen to it over and over again, and it will click. If you want it to, if you want to learn it, it will happen. It just takes a while to study this stuff.
If you don't have a copy of Refrigeration Air Conditioning Technology, it's Whitman, Johnson, Tom Zack. You can buy used copies on Amazon Books or eBay, or you can even sometimes get them from instructors at high school programs or college programs. Pick a copy of that textbook up. Chapters 1, 2, and 3 are probably the ones that everybody should have learned, but everybody sort of skipped over when we were in school. And then download this chart, this target temp split chart. It's got also some really good charging charts in there for fixed orifice metering devices. And there's a whole guide on TruTech Tools about how to properly charge a system. And I wrote it up, 4 or 5 years ago. And actually, it's in the top of Google searches for charging an air conditioner. And that'll be helpful too. But there's a ton of links in there and a ton of free information that'll help you out.
Well, that's fantastic. So sorry, guys, I couldn't say like 17 degrees is what you should be doing. That would be too easy, I guess.
Yeah.
Or 18 degrees or whatever.
Yeah. No, it's definitely not. Pick up the chart, use the chart. You'll be much better off, and you will save your customers a boatload of money. And by the way, if you get this chart, use it on your own home first, because it'd be nice for you to save some money too. And most of us don't think about that, working on our own home system enough. Just getting that airflow correct, getting your sensible latent split right, getting it optimized for airflow will save you a ton of money, because that equipment's going to satisfy the load and shut off. That's the best savings you can get, is when the air conditioner's not running.
That's exactly right. Maybe we'll have another brain-busting seminar here one day. I enjoyed this immensely, so I hope we get to do it again soon. Thank you all for joining me for The Tradesman. In the coming weeks, we're going to have Eric, HVAC Junkie from YouTube, out there in California. He's going to tell us all about his trade school and unions. And Alexander Figueroa, coming up next week, he's going to talk to us about what it's like to do HVAC in Puerto Rico. So there's plenty of interesting stuff coming up on the business side, on different trades. We're going to do some refrigeration, get back into some electrical stuff, and I hope we're going to get some plumbing guys on here real soon to talk to us too. As always, if you like what you've heard, please share it on Facebook. Share it any way you can so we can make this podcast grow. It all depends on you guys and whether or not you're into it or not, and I hope that you are. And if you need me, you can find me here on The Tradesman each week on Saturday morning, or email me at ZacharyPsioda, ZacharyPsioda @gmail.com. Thank you guys, and I'll see you on the next one.